We'll move on now to the last talk before we go to our first breakout session, which is given by Tom Sturgeon from Immaterial, spin-out company based near Cambridge, and it's tailoring filtration materials to remove challenging pollutants. So I'll hand over straight to you, Tom. I can see your screen, but I can't hear you.
Yeah, I forgot to take myself off mute. Thank you very much. And thanks for the opportunity to talk here in the TAPAS meeting. I've really enjoyed the regular meetings we've had over the last year. So hopefully I can share something interesting with everyone today. As was mentioned, Immaterial's a company spun out from the University of Cambridge, and we're still based here in Cambridge on the Science Park. Still quite a small company, and we work with porous materials, using both computational and empirical methods to develop these materials into a range of applications. Our key applications you can see here on the bullets. The lead applications really around cleaning air for breathable air applications. We're also looking at hydrogen supply, both purification and storage of hydrogen, looking at CO2 capture, which is obviously a couple of trendy topics there at the moment. And the last area for us is around efficient cooling for HVAC systems as well. So I'll first tell you a bit about the materials that we work with, and then I'll share some of our recent results. So the porous materials that we predominantly work with are known as metal organic frameworks, and they compare to traditional porous materials, which are essentially porous rocks or porous charcoals. And metal organic frameworks, here we've got them illustrated by these sort of spheres and the cuboids, are to an extent what the name suggests. They're these framework structures built up by metal species represented by the spheres, and organic ligands represented by the cuboids. And by choosing the metal and the linker, we can design these structures at a molecular level. That means that there's a huge amount of variability, choosing different ligands, choosing different metals, potentially mixed ligands and mixed metals, and even post-synthetic modifications. And overall, being able to control and design things at this molecular level allows us to really target specific molecular species. So that means that we've got 100,000 known structures that we can work with. And from an application point of view, in the air cleaning space, this means that we're looking to adsorb gaseous pollutants as opposed to particulate matter. Just sort of referring back to the hierarchy of cleaning technologies that Nick shared earlier, I think this puts us in the mechanical filtration bucket alongside HEPA filters. So HEPA filters kind of providing a mesh which traps particulate matter. Traditional porous materials, typically activated carbons, provide pores for gases to adsorb onto, and you can think of metal organic frameworks as a more sophisticated activated carbon. One of the challenges with adopting metal organic frameworks has been around forming them and integrating them into practical systems. So the same sort of fine synthetic tunability that they've got has meant that they end up typically forming as fine powders, and you can imagine anything with a gas flow doesn't work particularly well with fine powders. Traditional pelletization techniques with these fine powders haven't really worked, and that's where Immaterial's technology comes in. So you can see this picture on the left. We've got some examples of our what we describe as the Monolith, which is a fully crystalline pellet. So the efficient packing that we get within these monoliths allows us to achieve 4 times the volumetric performance of the powders within a system. And it's a technology that's worked with every metal organic framework structure that we've tried to date, which is some tens. So we're hoping it works with all 100,000, but we certainly haven't tested it with all of them yet. And then, as I said, this monolith has allowed us to work with partners in lots of different application spaces, but particularly air cleaning applications to integrate it into real world systems. So focusing on these breathable air applications, We're doing a lot of work looking at cleaning air in sort of living spaces, so somewhat focused at homes, but probably a lot of very relevant challenges for schools as well. Here we've focused on ammonia, formaldehyde, and NOx as initial gaseous pollutants, but in principle, we could look at other gaseous pollutants in that environment as well. And it's particularly some of our NOx data that I'm going to share in a moment. We're also working with the Ministry of Defence here in the UK and the Department of Defence to build our materials into gas masks, and that's really targeting some specific small toxic industrial gases which are of concern there. And then in cabin environments, we're looking both in automotive and aerospace cabin environments. So in automotive, there's new cabin air quality legislation coming in. And then on the civil aviation side, it's something that I never really thought about until I started reading about it. But now thinking back, I've always felt that airplanes do have a very distinctive smell, and it turns out that those smells that you might recognize with an airplane are known to link to certain compounds, which again, these traditional porous materials don't clean up so effectively. So that's what we're looking at there. Lastly, on the cabin air, there's also a lot of interest in increasing the recirculation of cabin air. So if we can increase the recirculation, it will require less conditioning, either heating or cooling of the air to maintain the cabin environment. But if you do recirculate the air, you see moisture and CO2 buildup, and that's another area of, so specifically CO2 and water, that we're developing materials to really effectively remove. So going into a bit more detail of domestic air cleaning applications, the way that we typically work, because these materials can be described on a molecular level, it allows us to conduct simulations on that molecular level as well. So a computational description of the chemistry of the metal organic framework, as well as the pollutants that we're interested in, allows us to look at this landscape of 100,000 structures. Typically, we'll down select to a relevant subset of those structures. In this case, we whittled it down to just about 1,600 structures that we felt were relevant to look at in an indoor environment. And then doing those molecular simulations allows us to generate these box plots on the right hand side. So there's a vertical axis not shown in precisely here, which is volumetric capacity. And so basically each of these circles is a different metal organic framework that we've simulated, and the higher up it is, the better the performance we'd expect against the three gases that we simulated, so ammonia, formaldehyde, and NO2. The experimental data that I'm going to show you in a moment is with one of our products, which we described as MOF2, which sat somewhere really in the middle of these box plots. But you can see highlighted here MOF18 as well, which is right up at the top end of the structures that we simulated, is another material that we're very excited about and have been working on. So the materials that we've selected for out of these 1,600, we're particularly focused on things like the chemical safety of those materials, as well as the expected cost of production if it makes it to commercialization as well. I guess one last thing worth highlighting on here, we've talked about these things as MOF2, MOF18, that kind of stuff. Those are internal codes for Immaterial, and only worth highlighting because the academic literature has adopted some similar naming conventions for specific structures, and our naming convention here doesn't correspond to those. So we really need to come up with proper product names, but that's probably a challenge for another day. So to share some of our experimental data now, as I said, this is for our material MOF2. So this is the kind of controlled laboratory testing that Nick was talking about earlier, which certainly doesn't give a full picture, but is our initial go-to to start to understand the performance of different materials. So in our test rig setup here, we've introduced NO2 at 10 ppm. And then on the back end of the filter bed. We've got a total NOx detector, and the temperatures, pressures, and flow rates that we're using are typical for a domestic type of fan. And just to explain what you're seeing on these graphs, so if I go to this graph in the middle, this is introducing that NO2 stream, and the percentage that you're breaking through is where this line's plotted. So when this line reaches the top, that means all 10 ppm is breaking through the filter bed. And the two plots here, the AC, that's standing for activated carbon. So we extracted activated carbon from a commercial filter unit and compared our MOF2 to that activated carbon. So you can see a similar sort of shape profile to our MOF2, but really what we've got is around 3 times the capacity to the activated carbon that we extracted. So the total area above these curves gives you an idea of the total amount of, or does give you the total amount of NO2 that's absorbed. We didn't, the gas stream that we used didn't have any humidity, but we did do external testing with humidity, again, for the same activated carbon and the same metal organic framework, and saw essentially the same performance. So humidity doesn't seem to have an impact. And then we're working with some of the leading providers of these sorts of fans in the UK and Europe, and the test data that they've shown or shared with us from the materials that we've sent to them is again sort of backing up what we're seeing with our internal testing. The 3 times capacity that we've seen here, we went to the academic literature as well to try and understand, is it just that specific activated carbon from that product that isn't as good? Are there other things out there? It's very difficult to compare our test results to what you're seeing in the academic literature, because you need all of the conditions to match up. So with a fair sort of caveat that it's hard to compare, from what we could see in the literature, we think we've got about 2 times the capacity of other activated carbons that are being tested in the academic literature. And if I just jump back, I highlighted this MOF18. If you look here at NO2, this is actually a logarithmic scale again, so a bit annoying that it's not on here, but we'd expect a substantial performance for NO2 with MOF18, and potentially some good multi-pollutant performance. So that's this last comment here, that we've got a next generation material, which from our computational simulations should have enhanced capacity again. And the last thing that we've done on these breakthrough tests was looking at the desorption. So now switching over the air flowing through from 10 ppm of NO2 to just a clean airflow. And here what we see is the activated carbon is now giving off quite a bit of NOx. And in contrast, the MOF2 is under these conditions is holding on to the NO2 tightly. One last thing worth mentioning on this slide, and that's kind of relating to some of the comments about the higher risk technologies. One thing we have to be very aware of is potential surface chemistry on these adsorption materials. So NOx is quite a reactive species, and actually with the activated carbon, you initially see a peak of NO rather than NO2 coming through due to some surface chemistry. And again, that's something that we've been able to avoid with our metal organic frameworks, but hence the importance of having a total NOx detector on the end. Our next step of tuning these materials.
In view of the time, Tom, can you sort of wind up, please?
Yeah, I'm almost there. This is pretty much my last slide. So a bit more of the technology development. We can control the porosity profiles as well, and that's important for providing kinetics. So something else which has been mentioned today is the lifetime of these filters and how frequently you have to change them. So MOF2B, the orange one, was what I was showing you before. If we introduce, or if we remove all the mesoporosity, we restrict the kinetics initially, and you get approximately the same total absorption capacity, but you spread that out over a longer time. So if you can tune these materials to give you a certain cleaning threshold, but then have to change the filters less frequently, that could be attractive as well in some of these air cleaning applications. So next steps for us, we're doing some simulated real-world testing with Terry Dillon at the University of York, looking to get our products through product qualification, so really understanding all of that and hopefully getting them more towards market. And lastly, I just wanted to acknowledge my colleagues, Robin Babu, Nick Rice, and Aurelia Lee, who are the scientists who did all the work that I've just shared with you. I'll wrap it up there.
Thank you very much, Tom. I think there is a question in the chat about recharging your MOF. Perhaps you'd like to answer that. And I